Hello, this is lesson 4.4 and we are solving equations with logs and exponent functions. So we're going to do a quick review of what we've done so far. So true or false, x to the power 4 equals 15 is an exponential equation. So if we look at this equation right here, x is the base and 4 is the exponent. So since x is the base, this is a polynomial equation. Uh, so this one is false. Okay, next one. 4 to the power of x equals 15 is an exponential equation. Now, x is the exponent. So yes, that means that this is an exponential equation. Next one is -3 is a solution of log with base 5 of 9 equals 2 times log of base 5 x. Okay, so what we need to do here is we need to, of course, solve this. So log base 5, 9 equals, I'm going to bring that 2 here to as an exponent to the x. So log with base 5 x squared. Now, we have the same basis for the log. We can just rewrite this as 9 equals x squared. And when we take the square root, it's a positive and a negative. So x equals positive and negative, positive and negative 3. So yes, this is true. -3 is a solution. All right, next one. -10 is a solution of log base 5 of x plus 35 equals 2. So we're going to write this as an exponential equation. So 5 is the base, 2 is the exponent, and this equals x plus 35. So we're going to plug in the -10 as x. 5 squared equals -10 plus 35. And we know that 5 squared is 25. -10 plus 35 is 25. So it is true. So always remember to work smarter, not harder. Choose the easiest method to solve. That's kind of the key thing here. Okay, we're going to look at one-to-one property. This property applies to both exponents and logs. For exponents, if the bases are the same, then the exponents are equal. So if b to the power of m equals b to the power of n, then we can say that m equals n. And if 2 to the power of 4x minus 1 equals 2 to the power of 7, we can say that 4x minus 1 equals 7. So the exponents are the same. And now we can solve this adding 1. 4x equals 8, x equals 2. Okay? For logs, if the bases are the same, then arguments are equal. So we actually use that. Over here, we did 9 and x squared equal already. Okay, so natural log of 7x minus 23 divided by x plus 1 equals natural log of x minus 3. Now, what we're going to do is we're going to set 7x minus 23 over x plus 1 to equal x minus 3. So we're dropping the natural logs. We need to get rid of, again, this is a rational equation. So we want to move the x plus 1 or multiply by the x plus 1. So we're going to multiply this side by x plus 1, and we're going to multiply this side by x plus 1. Now, x plus 1's cancel out, and we get 7x minus 23 equals, and we're going to go ahead and FOIL this, x squared plus x minus 3x minus 3. Okay, now we're going to combine like terms right here, and move this 7x and 23 to the other side. So minus 7x plus 23. So what do we get? I'm going to write it. So I'm flipping the equals, the left and the right side over. So x squared plus x minus 3x is negative 2x minus 7x is going to be negative 9x. And then negative 3 plus 23. So this part right here is going to be plus 20. And actually, you know what? Let's just put the 0 where it was. So when we cancel these out, it's the left side is 0. I know I said that I was going to flip them. Anyways, I did not do that. So now we're going to factor this out, and our factors are going to be x minus 4 and x minus 5. These are set to equal 0. So x minus 4 equals 0, which gives us x equals 4. And x minus 5 equals 0. So x equals 5, and that should be an equal sign. Okay, so to answer our question, we can write it as a set 4 or 5 inside the braces, or we can give it as x equals 4 and x equals 5. All right, so practice. Solve each exponential equation by using the 1-to-1 property here. So what are we going to do with this one? What we want to do is so 2 to the power of x, we want to rewrite 64 as, or with the base 2. Now, 2 to the power of 6 is going to be 64. And now we can see that our bases are both 2, so we can say x equals 6. So again, 2 to the power of 6 is 64. That's where we get this. Okay, next one. 3 to the power of x equals 81. We're going to do the exact same thing. We're going to figure out, or write this with the same base. So on the left, we still have 3 to the power of x. 81 can be written with the base 3. It is 3 to the power of 4. So 3 to the power of 4 is 81. So our x is going to equal 4. Same thing here, 5 to the power of x. And we need to figure out 5 to what power equals 125. Well, that's going to be 5 to the power of 3. So 5 to the power of 3. And since we're using the 1-to-1, our bases are the same. So our exponents are going to be set to equal. X equals 3. Okay, next one. Again, we've got 5 to the power of x. We need to figure out 5 to the power of what equals 625. Well, that's going to be 5 to the power of 4. So 5 to the power of x equals 5 to the power of 4. So x equals 4. So I highly recommend, well, you know what, let's look at a couple of, or here, a couple of examples. But what you can do is you can pause the video and try these on your own and see what you get. So 2 to the power of x minus 1. Again, we want to rewrite 32 with the base 2. So 2 to the power of 5 is going to be 32. And now what we need to do is take the exponents. X minus 1 equals 5. So we're going to add 1, x equals 6. Hold on. I'm missing. I'm sorry. I just realized that I'm missing something. That's not correct. I was missing the 2x. Okay, let's try this again. So 2 to the power of 2x minus 1. I only wrote it as x minus 1. It's 2x minus 1. And then the 32 would be the 2 to the power of 5. Okay, now we take the exponents. 2x minus 1 equals 5. We add 1, and we get 2x equals 6, and we divide by the 2, and we get x equals 3. I'm running into the other one. Okay, next one. Um, 3 to the power of 3x plus 1, 27. We're going to rewrite that with the base 3, so that's going to be 3 cubed. Now, the exponent, since the bases are the same, 3x plus 1 equals 3. We're going to not add, subtract 1. And we get 3x equals 2. And it is x equals 2/3 because we're going to divide by 3. Okay, this next one, looking at it, we have 4 to the power of 2x minus 1 equals, and we need 4 to what power equals, okay, 64, that's going to be a 3. So 2x minus 1 equals 3. We're adding the 1, and we get 2x equals 4. Divide by 2, and we get x equals 2 as our x. Number 8, we have a base 5 and an exponent 3x minus 1. So we're going to rewrite 125 with the base 5. So it's 5 to the power of 3. And again, our bases are the same. So we're going to rewrite the exponents as 3x minus 1 equals 3. Add 1, and we get 3x equals 4. And divide by the 3, we get x equals 4/3. Okay, next one. Now, looking at this 32 and 8, we are not able to write 32 with the base 8. So we need to switch the basis for both. And one easy one would be a 2. So 2 to the power of 3 equals 8. And then 2 to the power of 5 equals 32. And then we need the x here. So 5x equals 3. We divide by 5, x equals 3/5. Same thing here for number 10. We have a 4 and a 32. Well, if we do base 4, 4 to the power of 4 is 4. 4 to the power of 2 is 16. 4 to the power of 3 is going to be 64. So you can see that 32 is not, we can't write it with base 4. So what we need to do is we need to switch the 4 to base 2. 2 to the power of 2 is a 4, and then we have to remember the x. And 32 is going to be 2 to the power of 5. So now we can set 2x to equal 5. We divide by 2, and we get x equals 5/2. Okay, next one, same thing. 9 to the power of x equals 27. So we can't write 27 with base 9, so we're going to have to do it with 3. So 3 to the power of 2 is 9, and then we've got to make sure that we remember the x, and 27, 3 to the power of 3. So 2x equals 3, we divide by 2, and we get x equals 3/2. Number 12, 125 to the power of x and 625. So both of these can be written with base 5. 125, we already did this. for example, right here, 125 and 5 to the power of 3. So we know that this is going to be 5 to the power of 3 and the x is going to stay. We did the 625 somewhere as well. So this is going to be 5 to the power of 4. So 3x equals 4, x equals 4 over 3. Now, the next one. We've got to be careful here. So we have the base 3, and exponent is 1 minus x. Now, 27 can be written as base with the base 3. So 3, it's 1 over, so it has to be a negative exponent. And 3 to the power of 3 would be 27. So 1 minus x equals negative 3. We subtract negative 1, and we get negative x equals negative 4. We divide by negative 1, so x equals 4. And then our example number 14, so 5 to the power of 2 minus x. That is already with base 5. Now we're going to rewrite 1 over 125 with the base 5. So our base is going to be 5. Since it is a reciprocal, it's 1 over, it's going to be a negative. And 5 to the power of 3 is 125. So 2 minus x equals negative 3. We subtract 2. Negative x equals negative 5. X equals 5. Okay, so use 1-to-1 property when you can. It usually is the easiest. The other one to use is the definition of logs when the variable is in one exponent. And usually if we use this, we give 4 decimal places as the answer. Okay, so example, solve for x to the power of x equals 10. So right now, looking at this, variable is in one exponent. It's right here. So what do we need to do? Definition of log. So we're going to go ahead and write this as a log. Log base 2 of 10 equals x. Next, we're going to do the change of base. So remember this, we're going to do natural log of 10 over natural log of 2. We actually should have used the common log because it is a 10. But anyways, you're going to have to plug this in the calculator anyways, and you're going to get 3.3219 as the answer. Okay, if there is one log statement, use definition of logs. So convert to an exponential equation is what it means. So again, a one log statement, common log of x minus 3 equals 4. So again, the base here is a 10 since it's not written. 10 to the power of 4 equals x minus 3. Well, 10 to the power of 4 is 10,000 equals x minus 3. We add 3 and we get 10,003 equals x. Okay. If there is more than one log statement, use properties of logs. Properties of logs. Okay, so we have more than one log statement here. So what we're going to do is, remember, if we have the same basis and then we have an addition, we can rewrite the arguments as a multiplication. So we can take the x and multiply it by this x plus 2, like this. And then our other side is going to be log base 2 of 6 plus 1. Okay, now we used the product property right here. Next, we're going to use the one-to-one. So this was the product property. So with the one-to-one, we can just write it as x times x plus 2. So we can take the arguments and just write those equals 6x plus 1. We're going to distribute the x, so we get x squared plus 2x equals 6x plus 1. We're going to subtract 6x and 1 from both sides. And we get x squared minus 4x minus 1 equals 0. Now, we need to factor this. We're not going to be able to actually factor. We're going to have to use the quadratic formula here. So ax squared minus bx, ax squared plus bx plus c. So our a is 1, b is negative 4, and c is negative 1. Quadratic formula is negative b, which in this case is negative 4, plus minus b squared minus 4 times a times c, and a square root of this, and then 2 divided by a. Okay, so what do we get? The negatives cancel out, and then inside here, we're going to get 16 plus 4, which is 20, square root of 20, divided by 2. Okay, we can take out, so 20 has factors of 4 and 5. Square root of 4 is going to be 2, and the 5 is going to stay inside as square root of 5 over 2. Now, we have a 2 here, we have a 2 here, and we can divide 4 by 2, so we get 2. So our answer is 2 plus minus square root of 5. Now, here's the important thing, though. We need to make sure that this works, or that both of these work. If we look at x plus, no, not x plus. Let's do x equals 2 plus square root of 5, and then x equals 2 minus square root of 5. What the values are. So when we do the calculations, 2 plus square root of 5, we get 4.236. 2 minus square root of 5 is going to be negative 0.236. This negative is not, we can't use this answer because we can't have a negative as a log. And if we plug this back in, for example, here, so 6 times negative, sorry, what am I writing? 6 times negative 0.236 plus 1 would be a negative, right? It would be a negative 0.1416. So we can't use this value because it's going to give us a negative argument, and that's not possible. So our only answer here is going to be the positive. So x equals 2 plus square root of 5. So you need to make sure that you go back and check that it actually works. Okay, if there are two exponential expressions, different bases, take the natural log of both sides. Let's look at this one. So we have 7 to the power of x minus 4 equals 5 to the power of 2. So what we're going to do is we're going to take a natural log of both of these. Oops. Like this. Then we're going to use the property again. We can bring these exponents to the front. So we can rewrite this as x minus 4 times natural log of 7 and 2 times natural log of 5. What we're going to do now is we're going to divide by natural log of 7 to move it over here. So we get, hold on a second, x minus 4 equals 2 natural log of 5 over natural log of 7. Now we're going to add the 4 to both sides. And x equals 2 natural log of 5 over natural log of 7 plus 4. And this is going to be 5.6542. Okay, these next problems here, 1 through 12, are going to be practice problems. What I suggest is that you pause the video and then, you know, see what you can get done on your own. To make this video a little bit shorter, I'm trying to think. No, actually, well, yeah, because I mean, you'll be able to rewind it. I was gonna shorten it and make 2 videos, but you know what? Let's just go ahead and get these done. Actually, you know what? No, I'm gonna do the odd examples here, and then I'll make a different video for the even ones. And that way I've got enough room as well for, you know, to solve these. Okay, 3 to the power of x equals 17. What we're going to use here, so we're going to use, look at what we just learned, you know, here, 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 and here. Now, looking at this, we have one variable in the exponent. So what we're going to do is we're going to use the definition of log for this one. Okay, so natural log of 3 to the power of x equals the natural log of 17. And then we're going to bring the x to the front. X times natural log of 3 equals natural log of 17. We're going to divide by natural log of 3 to move that to the right. So we get x equals natural log of 17 over 3, which is x equals 2.579. And that is going to be our answer. Okay, for this next one, number 3, again, we have one variable inside, or as the exponent, sorry, not inside. We're going to use the definition of logs, again, for this one. So ln 5 to the power of 6 minus 3 equals ln 2 for x plus 1. We can bring those to the front by our property. 6x minus 3 natural log of 5 and 4x plus 1 natural log of 2. Then what we're going to do here is we're going to distribute. So 6x natural log of 5 minus 3 natural log of 5, 4x natural log of 2 plus 1. So there's a 1 and then natural log of 2. So I distribute it. Now we want to move the ones that have the x to the same side. And then we're going to move the ones without the x to the right, L and 5. Okay, so these cancel out. We get 6x minus 4, no, 6x natural log of 5 minus 4x natural log of 2 equals 3 natural log of 5 plus natural log of 2. And what we're going to do here is we're going to take x as the common factor. So 6 natural log of 5 is left, and then 4 natural log of 2. And on this side, we're not making any changes right now. We're going to go ahead and divide by 6 natural log of 5 minus 4 natural log of 2 to cancel these. So the same thing here. And now we have x equals 3 natural log of 5 plus natural log of 2 over 6 natural log of 5 minus 4 natural log of 2. And we need to do that calculation. And actually, I realized that my key has a mistake, so I'm going to need a calculator to do this. Now, remember that when you're putting this in the calculator, that you put parentheses here, even though we don't do it, just so that the calculator calculates it correct. Or another thing is to press the equal button before you do the division. But on the bottom, you're going to have to put it inside the calculator or inside the parentheses. So you should get, actually, you know what? Let me do this. X is 0.8021. Okay, what I want to do is I'm going to do, so 3 times natural log of 5 is 4.8283 plus natural log of 2 is 0.6931 divided by 6 times natural log of 5, which is 9.6566, and minus 4 times natural log of 2, which is 2.7726. And now, if we do that calculation, we get on the top, I just want to make sure that my calculation is correct here. That's why I'm, is 5.5214 divided by 6.884. And that gives this number right here. Okay, and again, we're just doing the odds for this video, I will create another video for the events just because I want to make sure that, you can always do the events as we're going. But as you can see, I'm kind of going to the other side, and I feel like this is going to be a long video if I do the whole thing. Well, this number 5 is going to be easier. If we look at this, we have a log, and the x is in the argument, so we're going to use the definition of logs. So our base is 3, our exponent is 4, and that equals x. 3 to the power of 4 is 81. So that one was easy. Okay, next one, number 7, right here, is going to be, or what we're going to do here is we're going to use the product property. We have the same basis for the logs, and we have an addition. So we're going to rewrite this as log 5 x times 4x minus 1 equals 1. Now we can write it as an exponent. 5 to the power of 1 equals x times 4x minus 1. So 5 equals 4x squared minus x. Then we're going to subtract 5 from both sides, and we get 0 equals 4x squared minus x minus 5. This one we can factor. So, and again, you can always use the quadratic formula. I mean, you'll get the same answer. But again, we can factor this as 4x minus 5 and x plus 1. So we have 4x minus 5 equals 0, and x plus 1, not x equals, x plus 1 equals 0. So we add 5. 4x equals 5, divide by 4, x equals 5 fourths. And then we've got x equals, hold on, we are subtracting 1, so x equals negative 1. Now, notice that over here we have the log base 5 of x, which would be a negative. And this is not an option because we can't have a negative argument. So this is the extraneous solution. So our only solution is going to be x equals 5 fourths. All right, for number 9, we're going to use, again, property of logs. We can see that we have the same base 2, and we have a minus sign in between. So we can go ahead and write it with one log with a division. So x plus 2 divided by x minus 5, and this equals 3. Now we can write it as an exponent or exponential. So 3, hold on, not that way. 2 is the exponent and 3, no, sorry. 2 is the base and 3 is the exponent, and that equals x plus 2 over x minus 5. We're going to multiply by x minus 5, and we get x times x minus 5 equals x plus 2. So we distribute 8x minus 40 equals x plus 2. Subtract x, we get 7x minus 40 equals 2, add 40, and we get 7x equals 42. We divide by 7, and we get x equals 6. Okay, and that is for number 9. All right, next one. So we did not do this one. We did not do this one. I just want to make sure that in case somebody starts looking for those. We did not do those in this one. Okay, 11. Um, we are, again, we've got the same basis and we have a subtraction, so we're going to use the property of logs here. So log base 2, x plus 9 over x equals log base 2, x plus 1. Okay, well now we have the same logs, so we can use our 1 to 1 here and rewrite it as the arguments are equal. X plus 9 over x equals x plus 1. We're going to multiply by x both sides here to get rid of the x on the denominator, and we get x plus 9 equals x squared plus x. We're going to move the x here, which means that it actually cancels out on both sides. 9 equals x squared. We can take a square root of both, positive and negative. Positive and negative 3 equals x. Okay, so can we use both answers here, x equals 3 or x equals negative 3? Well, again, looking at this one right here, if we plug in negative 3 here, log base 2, negative 3, that's not, we can't have a negative there. So that's another extraneous solution. So our only solution would be x equals 3 for this one. Okay, so I'm gonna do the number 2 again, or number 12 again on the other video. So that would look, I mean, basically the same what we did with 11. And we're going to go ahead and look at applications. The total revenue for CVS Health in billions of dollars can be approximated by the function below, where x equals 7 corresponds to the year 2007. F of x equals 41.6 e to the power of 0.088x. Now, the question is this an exponential growth or decay? It is a growth, and it's a growth because the base is greater than 1. Remember that we're looking at the base. So e, the natural, natural number of e is that's greater than 1. Okay, B, identify and interpret the y-intercept. Use it to sketch the graph. So y-intercept means that we're going to set x2 equals 0. So 41.6 e to the power of 0.088 times 0. Well, any number to the power of 0 is going to be a 1. So we end up with 41.6. So this part here is going to equal 1. Again, that's the y-intercept. So let's start sketching here. So our y-intercept is going to be 41.6. Okay, what was the total revenue in 2011? So x equals 7 corresponds to year 2007. That means that 2011 would be x equals 11. Actually, I just realized, you know what? We did not, on B, it says interpret. We did not do that. So x is 0. That means that we're talking about the year 2000. So in 2000, the revenue was 41.6 billions of dollars. That's the interpretation of that. Okay, now let's go back to C. So x equals 11. So what we're going to do is what was the total revenue? So we're going to plug it in to that. F of 11 equals 41.6 e to the power of 0.088 times 11. Put it in the calculator and we get $109.5 billion. Okay, so um, what we're doing here is we're going to plug this number in here also. So we're going to say that 109.5 is somewhere here. Okay, we need to start doing the x-axis. What we're going to do is we're going to start with the year 2000, and that's when the revenue was 41.6 billion. And then we are moving up to 2011 here, and the revenue is 109.5. Okay, so our graph is going to look something, oops, did not touch the point, something like this. Next question is when was the first full year with which the revenue exceeded $140 billion? Okay, so what we need to do here is we're going to take the f of x, so 41.6 e to the power of 0.088x. We don't know what the x is. That's what we're trying to find out. This should be greater than the 140 right here. So we need to divide by 141.6 both sides to move things over. We get e to the power of 0.088x is greater than 3.3654. Now we have the x in the exponent. So what we're going to do is we're going to take the natural log and move this. We can, at the same time, we can move the exponent here to the front. Okay, now this right here is going to equal 1. So we're going to divide by 0.088 both sides. And x is going to be greater than 13.79 years. So what does that mean? What was the first full year? So the first full year would be 2014 because 13 is not a full year. So that's why it's going to be 14. Okay, we've got one more application here. So CVS health earnings per share in dollars can be approximated by the function below where x equals 7 corresponds to the year 2007. So we've got g of x equals negative 5.3 plus 3.54 natural log of x. I'm going to rewrite it with the natural, no, hold on. Natural log first because that's where the x is, and then the minus 5.3. Okay, so we need to use transformations to sketch a graph of the function. Okay, let's go ahead and make the graph right here. So our natural log function crosses the 0, 1 here, and it goes like this. Now, happens with our, so this is 1, 2, 3, 4, 5, 6, 7, 8. Um, 1, 2, and so on. Okay, so with the negative 5.3, that means that we are going down negative 5.3. So negative 1, negative 2, negative 3, negative 4. I'm going to have to add negative 5 and negative 6. So that is going to be right here somewhere, negative 5.3. So it's actually going to be this point because that's the point that is coming down. This one right here. So 1 and negative 5.3. Then we've got 3.54, which means that we're vertically stretching it, the natural log. So we're going to go ahead and we might want to calculate where, hold on. Sorry, I had a, so if, well, we can't calculate the, so, or, hold on, sorry, I'm totally like, we're not able to plug in a 0 here because it does not, that will be a domain error. Remember, we can't do a natural log of a 0. And we can see that it starts from here, so it doesn't even cross the 0 axis. What we need, though, is kind of to know where does it cross the x-axis, like where is that point? So, or what we can do is we can just kind of estimate that 3.54 and get try to get, where it's going to be a vertical stretch with it. But to kind of make sure, we can always do that y equals 0 equals 3.54 natural log of x minus 5.3. I'm going to add 5.3 to both sides here. So we get 5.3 equals 3.54 natural log of x. We're dividing by 3.54. So we get 1.497 equals natural log of x. Now, e to the power of 1.497 would equal our x. So let's see what we get. E to the power of 1.497 gives us 4.47x. So this is the x-intercept. So we are crossing the x-axis somewhere right here. So we can see that it does start kind of, keeps going and going and going like this. And this is our g of x. Because of the 3.54, remember that that is a vertical stretch. Okay, let's B. So year 2010, that means that x equals 10. So g of 10, we're going to plug that in, negative 5.3 plus 3.54 natural log of 10, and that is 2.851. So looking at our graph here, it goes a little bit too fast. It should be, if that's, well, the natural log is not correct either. Let's move, oops, did I erase the whole? There we go. So let's move our 2 up here and 3 up here. So now it would be, yeah, we're not, it's sketching. We're not doing it accurate, but somewhere there. Um, and then find the first full year in which the earnings per share exceeded 3.25. So the same thing that we did on the other one. So negative 5.3 plus 3.54 natural log of x is greater than 3.25. We're going to add 5.3. And we get 3.54 natural log of x. We are dividing by 3.54, both sides, and we get natural log of x is greater than 2.415. And now we can rewrite this as e to the power of 2.415, and that is greater than x. So 11.19 is greater than x. So the year 2012 would be the first full one. Okay, so that's it. Again, I'm gonna create another video for the even problems that we skipped. But if you've got any questions, let me know. Bye.